All right. So, this is why chemistry is useful. You can figure out how to charge your iPod. So, well, I mean, look at how they're dressed. Clearly, wasn't the cutting edge technology of the day. So, today's lecture is all about oxidation and reduction chemistry. This is a pretty broad category that includes combustion reactions, batteries, and a whole lot of corrosion and natural process type chemistry that takes place. It's sort of our catch-all category. We've talked about precipitation reaction. We've talked about acids and base. Redox covers a lot of other stuff. Like, it's a broad category that is sort of our catch-all. I'm going to introduce sort of two big ideas today, one of which is sort of important, focus thing where I'm going to ask you to do. Another one is a base, laying a foundation for second semester. So, oxidation and reduction chemistry is all about the transfer of electrons. It is electrons moving from one atom to another. Okay? So we have seen some examples of this kind of stuff. Anytime we have an ionic compound being formed. If you take two elements and you get them to react together and you form an ionic compound, that's an oxidation-reduction reaction. Okay? When we have a mixture of, say, copper wire, we take a copper wire and we dip it into a silver nitrate solution, and we have this change where the copper dissolves and the silver plates out. That's an example of a oxidation reduction. A transfer of electrons is what we're looking for. Typical sort of reaction would be to start with some silver nitrate in a beaker. It's a clear, colorless solution. And what we're going to do is we're going to take a piece of copper wire and we're going to stick the copper wire into the solution. Okay? At this point, the copper and the silver ions come into contact. Silver nitrate, of course, is actually silver ions and nitrate ions. When the silver ions bump into the copper, they will literally pull electrons off of the copper. And the silver will change into silver metal. We transfer an electron from the copper to the silver. That is the key thing that we look for in an oxidation-reduction reaction. The copper will dissolve into the solution, forming silver metal. You get a bunch of silver. Yep. So a key here is we're not creating elements. We're changing it from a solution, from an ion, into its elemental form. And yeah, it does form this really pretty silver metal. The thing to realize, of course, is that silver nitrate is more expensive than just going out and buying the silver. So, not a good way to make money. Yeah. So, there are two parts to this reaction. We have a reaction where we have something giving off electrons. In this case, the copper, right? The copper is forming copper ions, +1 or +2. We can sort of do it either way. The copper forms copper ions and gives off electrons in that process. Copper loses electrons. We call that process oxidation. Oxidation involves the loss of electrons. These are the two electrons that the copper lost. That's why it formed a +2 charge. Now we have another half to this. We have a situation where we have silver ions grabbing electrons, gaining electrons to form silver metal. We call this reduction. We say the silver is reduced. Okay? So oxidation involves the loss of electrons. Reduction involves the gain of electrons. Oxidation involves loss, OIL. Reduction involves gain, RIG. Oil rig. Oxidation involves loss. Reduction involves gain, oil rig. is a mnemonic that you can use to help you remember, hey, is this the oxidation part of the reaction or the reduction part of the reaction? Now, notice that neither of these reactions is complete. You have to have both of them happening at the same time. The electrons that the silver gains have to come from the copper. It takes both of these equations together to make a balanced chemical equation. We call these half reactions because it is half of the whole thing. Question? Because it's forming a +2 charge. Or probably a better way to think of it is it formed a +2 charge because it lost 2 electrons. And that would take 2 silver ions to do. You'd have to have 2 silver ions come and hit the copper. Questions? Emma?
I think this part where in the equation it's Cu plus AgNO3 and then it goes to Ag plus CuNO3 too.
Mm-hmm.
Wouldn't the Ag and the copper and the silver, not silver.
So, our overall reaction, right, is copper reacts with silver nitrate.
Yeah.
The nitrate's a spectator ion, it doesn't do anything.
How does it?
Okay? So what we want to think about for oxidation and reduction reactions is we want to look at, and you'll be given parts of these, okay? But you want to look at, what you end up trying to look at is, hey, what things attract electrons more strongly? Okay, does nitrate attract electrons very strongly? It has a negative charge. It's not going to happen. Nitrate doesn't form a precipitate. Nitrate is a very stable ion by itself, which is why it doesn't react and form precipitates. It's not going to react in oxidation-reduction reactions, those kinds of things.
But then what equation does the copper and the nitrate bond together?
Well, again, are they really bonded together, or are we just writing them that it looks like that? It's copper nitrate aqueous. So it's really separate ions. You're looking at what we call a molecular equation, right? And then we could break that down into complete or net ionic equation. And in the net ionic equation, it would look a lot more like this without the electrons. The nitrate would be left out.
So all oxidation and all reduction reactions are half reactions?
So oxidation and reduction are the two halves of the oxidation-reduction reaction. So oxidation reduction is both of them together. That's the complete reaction. Eden, did you have something or did I get it? All right. So oxidation and reduction are the two parts of an oxidation-reduction reaction. A lot of times we say redox, a redox reaction.
How do you calculate how many electrons like the Ag will be? Just based on its charge?
Charge. It's all based on the charge.
Okay.
Yep.
So can you ever have just oxidation?
Nope. Where do the electrons have to go from someplace and come from someplace. So they always have to be together. Now, one of the ways that we can make this whole sort of oxidation reduction stuff a little more sensible is by keeping track of the electrons. Because in those ones with charges and it was really clear what was going on, we could see that the charges were changing. But a lot of times, particularly with things like combustion reactions, this is an oxidation-reduction reaction. Electrons are being transferred from one place to another, but there's no easy way to see it. Okay? So what we want to do is essentially do some bookkeeping. We want to keep track of the electrons and keep track of how many electrons does this thing have. More importantly, how many has it gained or lost. So to do that, we use what we call oxidation numbers. And oxidation numbers and oxidation states are a lot like charges. Okay? Except we assign oxidation numbers to neutral elements or covalent compounds. Okay? And those oxidation numbers, the compound itself may not have a charge, but we sort of keep track of how many electrons it's gained or lost from its base state as a way to track where the electrons are going. If we see a change in oxidation number, we know that we've had a redox reaction take place. We've had a transfer of electrons in some way. So there are a few simple rules that we have to learn to be able to assign oxidation numbers. Okay? Rule number 1. If it's an element by itself in its natural elemental state, so for diatomics that's 2 of them together. For metals it would just be the metal by itself. Those things are given an oxidation state of 0. Okay, oxidation states or oxidation number for elements is always 0. Okay? Rule number 2. If it is oxygen in a compound, okay, a covalent or an ionic compound, oxygen almost always has an oxidation state of -2. Okay, so we're going to assign the oxygens oxidation states of -2. Rule number, oh yeah.
Because they're in a compound?
That's because it's in a compound. When they're in compounds, we assume that there is a chemical reaction that takes place to form them. That chemical reaction frequently involves a transfer of electrons. So in compounds, we assign oxygen a -2 oxidation state. Okay, whether it's an ionic compound or covalent compound is irrelevant. In compounds, they get a -2, with the small exception of what we call peroxides, hydrogen peroxide, potassium peroxide, those peroxide compounds. Oxygen has a -1 in those.
With CO2, you don't multiply the oxidation state number?
Each oxygen has a -2. And we'll get to sort of summing them up in a sec. Right now, we're just assigning the individual parts of the different compounds. Okay, rule number 3, hydrogens. Okay, hydrogens usually have an oxidation state of +1. In a compound, we're going to assign hydrogen an oxidation state of +1, except for a few rare hydride compounds. Did I? Okay, well, I'm doing that off the top of my head. I forgot to put a note in here about how I wrote it on the thing. So essentially what they represent is how many electrons has the thing gained or lost. Typically, oxygen gains 2 electrons. That's why it has -2 oxidation state. Elements haven't gained or lost any electrons. They're elements. They're balanced, so they get 0. Hydrogen almost always gives off an electron, so it gives them. Okay? Other elements, other things. If you have a monoatomic ion, that is an ion that comes as one atom as an ion all by itself. In other words, not the polyatomic ones. So something like sodium ions or fluorine ions or potassium ions or any ion, anything we have. An ion, it can be in a compound. It can be in sodium chloride. It can be in a compound. But your monoatomic ions, even in their compounds, get the same oxidation number as their charge. So if sodium has a +1 charge, its oxidation state is +1. Chlorine has a -1 charge, so its oxidation state is going to be -1.
But if that element is isolated, like for example...
So not when it's an element. If it's an element in its natural state, it says just sodium.
Yeah.
That would be 0.
Oh.
It says sodium chloride, the sodium's going to be +1, the chlorine's going to be -1.
So they're going to cancel out?
Yeah, and the charges will cancel out. That's an important part, because the next step is, hey, what about something like carbon? Carbon is really hard to predict. It doesn't form a normal charge. We say, hey, we know that this whole thing has 0 charge. That the oxidation number has to sum to oxidation numbers sum to 0. So if I look at methane, I know I have 4 hydrogens. Each one has a +1. So that gives me a +4 for all the hydrogens together. What does the carbon have to make it balance out to 0? It's got to be -4. So the oxidation number on carbon in this is -4 here. What's the oxidation? Well, we'll get there in a sec.
Wait, so you said that fluorine would have a -1 charge even though it's diatomic and not monoatomic?
No. Fluorine is a diatomic element, but it is a monoatomic ion. Right? When fluorine forms an ion, it doesn't come as always F2. It comes as fluorines by themselves. So elementally, when fluorine is an element, fluorine gas, that would have an oxidation state of 0. Fluorine ions, because they always form a -1 charge, would have an oxidation state of -1.
So if there are 2 oxygens with an oxidation state of
Yep. -4 oxidation state, so the carbon would have to have something to balance it out. Exactly. So what we want to do is that exact process. We want to think about what does the carbon have here versus what does the carbon have here? Because we're looking for, what we're really, really looking for is changes in the oxidation state. That's what's going to allow us to identify the oxidation reactions and the reduction reactions, is looking for changes in the oxidation state.
What ions aren't monatomic?
Polyatomics. Carbonate, sulfate, those are polyatomic. Yeah, no. I say monoatomic to distinguish them from the polyatomic ions. So, same reaction. Question?
I'm sorry.
Let's
So
go.
changes in oxidation state affect, that's what we look for when,
That helps us identify oxidation and reduction reactions. Occasionally, what I'm going to ask you to do is tell me what's the oxidation part of the reaction, what's the reduction part of the reaction. And then there are a few other special words I'm going to show you right now.
So if you ask us what's the oxidation part of the reaction, do we have to show this part where it's like Ag plus?
Yep, that would be right. And now we're going to get there. I'm going to show you how to do it. So, to identify oxidation and reduction, we go through and we use those oxidation number rules I just showed you, and we assign oxidation states. We've already got this. -4, +1, 0. Then the -2 for each oxygen meant that this carbon had to be a +4. Hydrogen is +1, oxygen is -2. So now we say to ourselves, what kind of changes happened? What kind of changes happened? And we say, hey, wait a sec, that carbon changed. Carbon went from -4 to +4. Okay? So, right, we went through and we assigned the oxidation numbers. We said each hydrogen is a +1, carbon has to be a -4 to balance it out. Then we came in and we said over here, each oxygen is -2. 2 of them gives me a -4 altogether. So the carbon had to be +4. So the carbon, during the course of this reaction, changed its oxidation state. It went from having a -4 to a +4. Its oxidation number went up. Okay, it went from -4 to +4. So that means that it lost electrons, which means it was oxidized. Oxidation involves loss of electrons. When something is oxidized, its oxidation number goes up, more positive. So we say that methane was oxidized, or the carbon was oxidized. And then we can also talk about what we call the agents, the agent of change, right? If you think about that phrase, agent of change, this carbon was the agent, the causative factor in something else being reduced. If the carbon was oxidized, if the methane was oxidized, that means it lost electrons. Those electrons had to go someplace, which means something else had to get reduced. So we say that carbon was or is oxidized, and it is the reducing agent. And the agent here means that it caused that reducing in something else by being oxidized. What was reduced? What had its oxidation number go down? The oxygen. Oxygen, and so oxygen oxidized. The reason why, because in a lot of cases, oxygen is the agent. It caused oxidation in something else. The oxygen went from 0 to -2. It doesn't matter that it's in different compounds. That's irrelevant for our purposes. We want to be able to identify where did the change happen. What thing was oxidized, what thing was reduced. And once we know that, then we can talk about what caused whatever. So if you are oxidized, you are always the reducing agent. If you are reduced, you are always the oxidizing agent. Because reduction means you gained electrons, something else had to lose them.
So whatever goes from negative to positive,
Well,
positive to negative, or
yeah, if the number goes up, it's more positive. But it could go from -4 to -2.
okay, so whatever goes up is
Yeah.
reduced.
And whatever goes down, no.
No,
Reduction is down.
yeah.
Okay. The number gets smaller. Reduced. That's nice because it gets smaller. Okay? All right. So let's look at a sample sort of problem here. Okay? We want to go through, and this is, I don't remember if this one is worked out for you already. I'm going to go ahead and work this one out because I don't think you're quite ready to do the problem by yourself yet, okay? So, but think about how you would do this as we go through it.
Should we write this in our?
This is, I think, the example box, but I'm going to sort of more work it through with you, okay? Just because I think we're on the edge of losing a bunch of people, so we're going to step through this a little bit. So step number 1, we have this reaction. It says lead 2 sulfide can be converted to lead 2 oxide by heating in an oxygen-rich environment. Sulfur dioxide is also produced. Identify the atoms that are oxidized and reduced, and specify the oxidizing and reducing agents. It's not that bad. What's our first step? What's the first thing we have to do? We've got to turn these words, lead 2 sulfide, and what does it mean? What else? What is the lead 2 sulfide reacting with? Yeah, the trick here is they said heating in an oxygen-rich environment. That means that there's lots of oxygen floating around to react with this. So do this. You can do this part, okay? Oxygen, this would be oxygen gas, okay? Convert these words. Give me a chemical equation, a balanced chemical equation. Okay, you can do that.
Would sulfide be S2?
Ide, the ide ending means it's just the element by itself.
So just S?
Just S.
Would it be S?
Yeah.
So then you have two of those.
Balance of charges.
What's the name on it?
What's wrong? Can't see? I think we could open, wait till we open some of those curtains in the back there. All right, so here's the balanced chemical reaction. 2 PBS, 3 O2s, 2 PBOs, 2 SO2. So now, your next step, okay? Your next step here is that you need to go through and assign oxidation states. So let's do that together. Nah, don't worry about it then. Their eyes will adjust. So, rule number 1, look for oxygens, or look for any element by itself. What oxidation state does an element all by itself have? Oxygen is, you got the oxygen, but when it's by itself, it's a 0. Okay? Now, we have some ions, right? This is essentially an ionic compound, right? This is going to be a +2 and a -2, because those are 2 monoatomic ions. Okay? Now, over here, same thing. Monoatomic ions, +2, -2. Sulfur dioxide, a little different. Sulfur dioxide is a covalent compound. This is not an ion. The sulfur here is not an ion. Okay? So, it is, however, a covalent compound. We follow the other rules that say, hey, oxygens in compounds have what oxidation state? That's where the -2 is. So, -2, and that, what is this? -2 times 2 gives me a -4. The sulfur has to be a +4.
Wait, what rule is that for?
So this is the last one where the oxidation states on the molecule have to sum to whatever the charge is. In this case, the charge was 0. So we use the oxygen to figure out what the sulfur has to be.
Oh, so you don't know what the
I don't know what the sulfur is because this is now a sulfur in a covalent compound. It's not an ion. This is not an ionic compound. And so that's where you can get a little tricky. It is possible to have a single element be both the oxidation and reducing, not what we did in this problem. So now we say, okay, what changes happened?
Sulfur.
Okay, so yeah, sulfur changed and the oxygen changed. So oxygen went from 0 to -2.
It's the reducing.
So was it reduced or was it oxidized? Did it? So oxidation, what is oxidation? Oxidation involves loss of electrons. Oil, oxidation involves loss. Did oxygen lose electrons to get -2? No. It gained. So if oxygen gains electrons, it is reduced. It is oxygen atoms are reduced, and oxygen is the oxidizing agent. Oxygen is almost always an oxidizing agent. Okay? It is, in fact, why it's called oxidizing. Oh. So, oxygen, right? Reduction involves gain. Oxygen gained electrons, so it was reduced. Its number went from 0 to -2. Its number went down, reduced, and it is the oxidizing agent. What happened to the sulfur? -2 to +4. Did it gain electrons or lose electrons? It lost electrons. Okay? Oxidation involves loss, so the sulfur was oxidized, and it is therefore the reducing agent. This is the level of stuff I'm going to ask you on the test. Okay? So the PB didn't change. The lead didn't change. It's actually not really part of the reaction, really. It's not a spectator ion. In fact, we didn't have, none of these are aqueous, so we don't have any spectator ions to worry about. Okay? Now, I want to introduce a concept, I want to introduce a process to you, okay, that is more complex, okay, that will help us second semester when we see all this stuff again in a different context. Some oxidation and reduction reactions are much more complex in terms of the way that we have to think about writing them and balancing them out. Okay? So, what we want to do is we want to go ahead and we want to be able to write and balance chemical reactions. And frequently those reactions we only know part of what's going on. So this is an oxidation reduction reaction where we have permanganate ions reacting with iron ions to produce a different kind of iron ion and a manganese ion. There are pieces missing of this reaction. These oxygens, where do they go? Okay? And these reactions actually happen in aqueous solutions, which is important because that means that we've got water floating around. And in fact, this one probably takes place in an acidic solution, which means we have hydrogens floating around. And so there's a process that we can follow to fill in these missing blanks, what we call the half reaction method, where we say, okay, I want to break this thing apart into the two halves. One half is going to be the manganese going to the manganese dioxide, or the permanganate, I should say, permanganate ion going to what? Yeah, it's going to go to the manganese. Now, what's the other half? We got the iron 2+ going to iron 3+. So notice I broke those in half. I broke them into two separate parts. Okay? One of these parts is going to be oxidation. One of them is reduction. Okay? This is my oxidation reaction. Oxidation involves loss of electrons. I went from +2 to +3. This one is going to be reduction. That's relatively unimportant for the rest of the process. Now, so step one, we broke the skeleton into two half reactions. Step two, balance anything that is not oxygen or hydrogen. Done. The manganese, 1 and 1. Iron, 1 and 1. Step three, balance oxygen atoms using water molecules. So for every oxygen I have over here, I want to have water on the other side to balance it out.
But where did those hydrogen?
We'll get there. We'll get there. Okay, so we're in an acidic solution. So step 4 is take this and balance the hydrogens using hydrogen ions. I'm telling you we're in an acidic solution, so there are hydrogen ions floating around. 4 times 2 is 8, so I'm going to add 8 hydrogen ions. Okay? Now, I'm at the point where I've balanced all the atoms. But these equations are still not balanced yet, because I have a lot of charge differences. I have to balance the charges. My next step is to balance the charges. So I'm going to take these two reactions. I'm going to say, what is the total charge on this right-hand side if I added up all the different ions and all the different things? It's only one of them. So I have a +2 charge over here. Now I look at this side and I say, wait, 8 plus 1s, and here I do have to worry about the coefficients. 8 plus 1s, that's a +8, but I have a -1, so this side is +7. Now, I balance charges by adding electrons. I'm literally going to add in electrons, because remember this is oxidation reduction. I'm looking at electrons going from one place to another. So if I have a +2 and a +7, I got to get the +7 down to +2. I can do that by adding 5 electrons. Question? H2O has no charge. Neutral, no charge. Nope, just add them. Now I can add them to the left or I can add them to the right. So that's kind of like subtracting electrons if it's giving off electrons. But basically I just add electrons to one side or the other of each of the equations. So when I come over here and I look at the iron for a sec, I say, hey look, +2 versus +3. If I want this to balance out, I got to bring the +3 down to the +2. So I'm going to add 1 electron over here. +2 +3 minus 1 is +2. Now they're both balanced in terms of charge. Final step in doing this process is to make sure that the electrons gained on this half reaction equal the electrons lost on the other one. And I do that by taking this whole equation here, right? And I'm going to multiply this entire equation by 5. So that's 5 plus 2s, 5 plus 3s, and 5 electrons.
Why did we do that?
I have to make sure that the electrons gained on the one side equal the electrons lost on the other side. Because now what I'm going to do is I'm going to put these two half reactions back together. Okay? I've put these two half reactions back together. The last thing, hey, let's make sure that things that are the exact same, I take them out. Electrons should always come out. If your electrons don't come out, you made a bad boo-boo. And you need to go back and figure out what happened. This is the complete balanced equation for this reaction. Okay? So the process. Pull whatever they give you apart into two half reactions. Balance anything that's not hydrogen or oxygen in the normal way. Balance oxygens using water. Balance hydrogens using hydrogen ions. Make sure that the charge is balanced by adding electrons. Make sure that between the two halves, the electrons gained and lost equal each other. Put everything back together. This is a really important process in electrochemistry to understand how batteries work and how all that kind of electroplating and all that kind of stuff happens. Okay? But we really don't need this in a deep way until second semester. But I want to introduce it so you can start to see, so that if I give you a little problem later on to remind you, you've got it in the back of your head when we actually get to that electrochemistry.
So the equation does not involve loss and gain of the electrons?
Well, it does, but the electrons all remain hidden. The electrons are, we don't have, the overall, the real equation that we write, you should never see electrons in here. It's only when you break them apart into the individual halves. Because the electrons gained here should always equal the electrons lost here, so they should always cancel out. So you could also be in a basic solution, in which case you do a slight little change at the end, where, see all these hydrogens? We say, hey, I have 8 hydrogens. I'm going to add 8 hydroxides. And I add 8 hydroxides to each side, and the hydroxides become water, and then I'd have 8 hydroxides over here, and I'd need to do a little canceling with the water. But generally we work in an acidic solution, but you could work in a basic solution, and it's a real simple change. You do everything the exact same, and then you just get rid of the hydrogens by adding hydroxides at the end. Okay? All right, you want to give this a shot? Okay. So, a bunch of random stuff we don't care about. Part of a reaction, right? A part of a reaction. And we want to balance this equation. Okay, again, we're laying a foundation here. This is good to practice. Please don't panic. We're not in danger or in doubt. So it is not time to run in circles, scream, or shout. You should what? Well, these are ions written as ions, right? So this is potassium dichromate, but I've left the potassium out. Why do you think I left the potassium out? Because it doesn't matter, because it's a, what kind of ion? Spectator ion. It's not participating in the reaction. The potassium. You do. Well, what is it? Break it up in what way? You want to break this reaction apart into two halves. Do that. Not in thirds. No thirds. See the chromium here? So take this molecule. What did it turn into? Chromium 3 plus. See the carbons here? What did this carbon stuff turn into? CO2. We'll worry about oxygens. The process takes care of oxygens and hydrogens. We don't have to worry about that because the process is going to take care of those for us. Do you remember that? We have that. The process will take care of those ones. This is a process where we're figuring out how to balance it. This whole system, the whole long system, is about getting to a balanced equation. Don't worry about trying to balance it now. We're just going to go through and do the process. Step 1, break it apart. Dichromate and chromium, and that's one part. My other part is going to be ethanol to carbon dioxide. Now, that was step 1. I broke it apart. Now I balance things that are not hydrogen or oxygen. Balancing things that are not hydrogen or oxygen. So I have 2 chromiums here. So we better put 2 over here. What about I have 2 carbons? That's carbon's not a hydrogen or oxygen. So what do I got to do over there?
2.
Right. Now we say the next step is to balance oxygens by adding waters. How many oxygens do I have on the left-hand side? So what do I get over here? 7 H2O, 7 waters. Okay? Here it's a little trickier. I've got how many oxygens on this right-hand side? 4. And I've got 1, so I need 3 more. I'm going to add 3 more waters on the reactant side over here. You just add the waters wherever you need them to make it work. I have 2 and 2 is 4. I have 1. I need 3 more. This is why there's a really big box for this example. Okay? I'm not going on. Just, are there any questions? We broke it apart. We balanced things that weren't hydrogen or oxygen. We balanced oxygen by adding waters. Wherever we needed to add some waters, we added some waters. Next step is to balance hydrogens using hydrogen ions, H plus ions. So we go through and we count and we go, I got 7 times 2, so I need 14 hydrogens. Now over here is a little, we got to count. 3 times 2 is 6, plus 6 more is 12, and I got none over here. So I'm going to put 12 hydrogens. I know it's a lot of writing. These things, they just take up a lot of space and there's a lot of writing involved. We put 3 H2Os here because we had 3 plus 1 more is 4 oxygens. To balance out the 2 times 2 is 4 oxygens in. It is possible to, I'm showing you every step, but a lot of times you can just take the half reaction and make it grow on one line. Just keep adding stuff on each side as needed, if you had enough space. But this helps us see exactly what we did in each step, right? So now the next step is we got to balance the charges using electrons, right? So the next step is we're not trying to link them together yet. We're looking at this one and we're saying, what's the total charge on this side? 14 positives, negative 2, that gives me a plus 12 on this side. And over here I have 2 and plus 3, it's plus 6. So plus 12 and plus 6, I have to do what? 6 electrons over here. Same sort of thing over here. Here I have 12 pluses and nothing on the other side. So I need to add 6 electrons over here to balance out. And on this side I got 12 electrons to balance out the 12 hydrogens. So we added electrons to make sure the charges were balanced in each of the separate ones.
What's the charge on the two CR?
So Cr3 plus times 2 plus 6 all together. Multiply this one by 2. Why would we do that? So that the electrons gained and the electrons lost are the same. So we're going to take this equation right here and multiply it by 2. That means that we'll have 12 electrons, 28 hydrogens, 2 dichromates, 4 chromiums, and 14 waters. I need this number of electrons here to equal this number of electrons right there. Nope, we don't need to do anything to the one on the right. You generally multiply one or the other. You don't multiply both in general. But if you needed it to get it to balance out correctly, you could multiply both of them. But that's uncommon. Then we add it all back together. Okay? We add it all back together. Again, I'm laying a foundation here. The test, the rest of our work is going to focus on identifying oxidation and reduction reactions.
Oh, so you subtract the water and
Then I canceled stuff out. So if I have 3 waters here and 14 here, they're going to cancel out.